Hello everyone. In the last class, we were discussing about grading of cables. We are discussing about that. Okay. And told that there are two methods of grading. First one is yeah, capacitance grading, and second one is yeah, intersheath grading. So before discussing them into detail, let me have a very quick recapitulation about the grading of cables. By grading of a cable, it is meant that the distribution of dielectric material should be such that the difference between the maximum gradient and the minimum is reduced. That means grading is applied in order to reduce Gmax minus Gmin, this whole thing. Okay, it should be reduced. Thereby, a cable of the same size could be operated on at higher voltages, or for same operating voltage, a cable of relatively smaller size could be used. Okay. Now, there are two methods of grading, as already I have mentioned. The first one is capacitance grading. Here, we generally use more than one dielectric material, more than one dielectric material with different epsilon. Okay. And the second one is intersheath grading. Here, same dielectric material is used, but potentials potentials at certain radii are held at certain values by using intersheaths. Okay, by using intersheaths. What is intersheath? Thin metal sheets. Okay, so let's discuss about them one by one. So first we will be discussing about capacitance grading. So to explain that, one explanatory diagram is required at first. The radius of the core is r. We are assuming one uh, circular cross section at a distance x from the center, and the overall radius is capital R. Now again, let Q be your charge per unit length, charge per unit length. Okay, so if we have one single dielectric material, then gradient at the radius x, what will be that? G equal to q by 2 pi epsilon x. Okay, so where epsilon is the permittivity, it is known to you. And so if we could use an infinite number of materials, if infinite, or again indefinite permittivity materials are used, then what happens? Epsilon equal to k by x. Okay, if you use an infinite number of materials with varying permittivities given by epsilon equal to k by x, varying permittivity is used, such as epsilon equal to k by x, then G becomes what? Q by 2 pi k by x into x, that is equal to q by 2 pi k, which is actually a constant. Q is a constant 2 pi k. Okay, so what is the catch? Catch is the permittivity and distance are inversely proportional. That you have to remember. You have to place the dielectric layers in such a way that with increase in their distance from the core, the permittivity of that material should decrease. So you have to ascending order of permittivity materials depending on the increase in distance. So as the distance increases, the permittivity of the material should be low. So you have to arrange those materials accordingly. Okay, so basically what we are doing, for a particular operating voltage, the overall size of the cable becomes minimum, and this looks quite good, but practically it is impossible to place infinite number of dielectric material layers with varying permittivities. Okay, now normally 2 or 3 materials are used in general. Okay, let me write that. Practically infinite, not feasible. So 2 or 3 different materials may be utilized. Okay, that is the thing. That is the scenario. Now let at radius, and it's already r, r1 and r2 dielectrics of epsilon 1, epsilon 2 and epsilon 3 are placed. Okay, so let the dielectric strength, again let me change my ink. let dielectric strength is chosen as capital G1, capital G2, capital G3. Accordingly, working stresses is chosen as small g1, small g2, small g3 respectively. Okay. Now what is our main goal? Our main goal is we can't keep any material anywhere. Okay, you have to have a special arrangement. There must be some criteria, otherwise the grading cannot be utilized. Okay, the concept of grading will be meaningless. So suppose our objective is to obtain a uniform stress distribution. If this is your stress, this is your radius, there should be uniformity. Okay, and for that are at various radius with different permittivities having different dielectric strength and working stress. We cannot put them arbitrarily. We have to have a certain possibility, have to have obtain a certain pattern, and that pattern may be done either using two possibilities. So there might be two possibilities of above arrangement. Okay, possibility number one: factor of safety factor of safety is same for all material, and second possibility is same working stress for different material. Okay, we will analyze them one by one. Okay, so first we will be discussing about case 1. So for that, factor of safety for all the materials are the same. Gradient at conductor surface, gradient at conductor surface. Now what is that? See, it is q by 2 pi epsilon 1 r, and factor of safety is what? Dielectric strength, same factor of safety, g1 divided by f. F is factor of safety. In this case, F is safety factor. Okay, so that is the scenario. At okay, so that is happening in the conductor surface. Then we discussed that there are various radius r1 and r2. Okay, gradient at a radius r1, that will be what, q by 2 by epsilon 2 r1, and its working stress is g2. Factor of safety is same for all materials, so it is g2 by f. Similarly, gradient at a radius r2, the gradient will be q by 2 by epsilon 3 r2, and it will be g3 by f. Okay, so basically we have an arrangement. This is your core, this is your radius r1, this is your radius r2, this is the overall radius capital R. So this is R, this is R2, this is R1, this is R. Now this is actually your core material. From core to layer 1, the permittivity is epsilon 1. From layer 1 to layer 2, permittivity epsilon 2. From layer 2 to layer 3, permittivity is epsilon 3. And here the relations are there for working stresses. Okay, it will be clear. First refer to the diagram, then again go with these expressions that I have obtained for same safety factor. Okay, so from all these relations, suppose this is equation number 1, this is equation number 2, and this is equation number 3. So it is my request that you also practice the relations that I am deriving right now. So from 1, 2 and 3, what we can get is that q equal to 2 pi epsilon 1 into r into g1 by f equal to 2 pi epsilon 2 r1 g2 by f equal to 2 pi epsilon 3 r2 g3 by f, as f is common in every expressions, so we can write epsilon 1 r g1 equal to epsilon 2 r1 g2 equal to epsilon 3 r2 g3. Okay, so this relation you should remember when possibility number 1 is there. Now from this relation, if you can remember this relation, then go with the diagram. Here from the diagram it is evident, from diagram it is evident that epsilon 1 g1 is greater than epsilon 2 g2 is greater than epsilon 3 g3. Okay, so this is your relation. Okay, so from the diagram, okay, why I am writing this, and it is evident in this one. See, if this is your relation, epsilon 1 rg1 epsilon 2 r1 g2 equal to epsilon 3 r2 g3, and from the diagram it is evident that r less than r1 less than r2, so r2 is more than r1, r1 is more than r. So if you apply that concept over this equation, then obviously this epsilon g1 product will be greater than epsilon 2 g2 product, and it will be greater than epsilon 3 g3 product. Okay, so what is the meaning of it? It means that material with highest product of dielectric strength and permittivity should be placed nearest to the conductor, and the other layers should be in the descending order. So it is a very popular MCQ also, be careful with that. Therefore material material with highest permittivity dielectric strength product is placed near to the core. Okay, other layers are placed by a descending arrangement. Okay, now let's come with the possibility number 2. Second possibility. So it states about when all the materials are subjected to same maximum stress. So in this arrangement, Gmax is same. Gmax equal to Q by, again we will be considering the same layer. You can refer to the same diagram, this diagram, but the condition scenario is changed. So because now the maximum stress is same for all, so Q by 2 pi epsilon 1 r equal to Q by 2 pi epsilon 2 r1 equal to Q by 2 pi epsilon 3 r2. Okay, so if this is the scenario, then from this equation we can easily write that epsilon 1 r equal to epsilon 2 r1 equal to epsilon 3 r2. Okay, so we can have again for the from the diagram that r is less than r1 less than r2, or in other words r less than r1 less than r2. Okay, for your convenience I am drawing the diagram over here too. So this is your r, this is your r1, This is your R2 and this is overall capital R. So now it is evident that R is less than R1 less than R2. So therefore epsilon 1 is greater than epsilon 2 is greater than epsilon 3. Okay. So dielectric layer with highest epsilon is placed near to the core and other layers are arranged by descending orders of epsilon. Okay, so what happens if you want to have a plot? You can easily say that as equal number of maximum stress is there, so maximum stress in each case is same, so the stress distribution will also be the same. Epsilon 1 R1 product, this one again, this will be equal to epsilon 2 R1 product, and this will be epsilon 3 R2 product. So the capacitance grading voltage distribution will be more or less like similar. Okay, so the distribution of voltage using capacitance grading is given here. Now total operating voltage of the cable, total hatched area, that means the total hatched area. So let us derive that. Total operating voltage of the cable, total operating voltage of the cable with Gmax working stress, we got V equal to Gmax R ln R1 by R plus for layer 2 Gmax R1 ln R2 by R1. You know the formula V equal to G X ln R by R dash. Now for the first layer, in each and every case the stress G is same, so that is equal to G max. Now for first layer the distance is smaller, the higher distance is R1 and R dash is R, so I have put them because we are taking, okay, for your benefit, simplicity of understanding, I am writing G X ln R by R, that is the formula. So for first layer R is R1 and small r is R. For second layer R is R2 and R is small r1. On a similar analogy, for the final layer it is G max R2 ln capital R by small r2. Okay, so here G max becomes R ln R1 by R plus R1 ln R2 by R1 plus R2 ln capital R by small r2, this amount of volt. Okay, so this is the expression for voltage, you should remember. Okay, now we'll be talking about intersheet grading. R, R1, R2, and capital R. So we have to use a transformer here. This will help in maintaining different layers at different voltage levels. So this is voltage level V. There is another voltage level V2. Then comes V1. And the outermost layer is placed at ground potential, that is 0 volt. Okay, this is R, R1, epsilon 1. Okay, same material, so epsilon. So we have discussed while discussing about intersheet grading, same materials but different layers at different potential. So if permittivity will be same for all the layers. Epsilon R2, epsilon capital R. Okay, now these things, now in the earlier discussion, if you go to the diagram, if you go to the diagram of the earlier discussion, we will be observing that here in this case, these were different layers of dielectric. So one type of material, second type of material, third type of material. But in this case, material is same throughout, only metallic sheets are inserted. So this thing this thing and this thing, they are metallic sheet. Okay, now it is evident that an auxiliary transformer is used to maintain the metal sheet at the power conductor at certain potentials. As a result, stress distribution is different from one layer to the other, which it would be without the intersheaths. Now the objective is to show that the gradient with intersheath will be smaller than the gradient without intersheaths. So we know that if no intersheaths was not there, if you compare this particular cable with this one, the whole thing, it is R, it is capital R. There the stress distribution was ununiform. But here without intersheath. But here intersheaths are placed, and we have to see that the stress distribution is better than the blue one case. Okay, that means the stress distribution with intersheaths is better than without intersheath. That we have to see. Okay, so the cable remains same with core diameter and overall diameter. Only we have taken intersheaths at different locations. As a homogeneous material is used, the maximum value of stress at various intersheaths is same. Material is same, epsilon is same. So as being a homogeneous material, the maximum value of the stress, that means Gmax will also be the same. So I am writing that too. We use same dielectric sheets at different distance. Sheets are at different distance. Okay, so what happens? Gmax for different layers is same. Gmax for different layers is same. Okay, so assuming thickness of material, assuming thickness of material as R1 by R equal to, that means the sheets are placed in such a way that their ratios are small. I mean the same. This R1 by R, R2 by R1 and capital R by small r2. The ratio is same. We are assuming that R2 by R1, R by R2 equal to constant. Say it is a alpha. Okay. So with this arrangement, the Gmax at surface, Gmax at surface, that will be what? Gmax at conductor surface. You know the formula. Voltage difference between the two layers, V minus 0. In previous case it was V, the line voltage, and it was at ground potentials are 0, so it was V minus 0 equal to V. But right now this layer is at V, and you can see it is given from the transformer. This layer is at V, this layer is at V2. So it is now V minus V2 divided by X ln R by R. What is X here? X here is the R itself. So R ln. What is capital R? Capital R is R1 here. R1 by R. If you are unable to understand what I have derived here, you can pause and come back to the go back to the go back to that particular moment when I was describing this that okay. As it is a video lecture, you have the facility of having pause, forward, backward, everything. So do that. Now for the layer 1, therefore at at other layers, we can write that Gmax equal to, for the next layer, now we are talking about this layer, so it will be your R1 and R2 relation. So it will be, what will be the voltage difference? V2 minus V1. So it will be V2 minus V1 divided by R1 ln R2 by R1. And of course, for the last layer, this is V1, this is 0, so V1 minus 0, so V1 only. So it will be V1 divided by R2 ln capital R by small r2. Okay, so this is the scenario. So these three things are same. Gmax. So what we can write is that V, basically this is also Gmax, this is also Gmax, and this is also Gmax. So we can write that V minus V2 by R ln R1 by R equal to V2 minus V1 by R1 ln R2 by R1 equal to V1 by R2 ln capital R by small r2. Okay, or in other words, V minus V2 divided by R ln, you know the ratio is alpha, we have already assumed here. These ratios are alpha. This is equal to V2 minus V1 by R1 ln alpha equal to V1 by R2 ln alpha. Ln alpha is a common factor among all of them, so we can have that V minus V2 by small r equal to V2 minus V1 by small r1 equal to V1 by R2. Just a notice, you may not remember, just a relation. So we want to compare the gradients under the two conditions, therefore we must express them in terms of capital V, small r and alpha. So to find the gradient with intersheets, let us express V1 in terms of V2 and V2 in terms of V, just like what we have done in overhead transmission line in capacitance grading. There you have V1 and V2, and there is a factor K, V2 equal to 1 plus alpha K, V3 equal to 1 plus 1 plus K into 1 plus 3K into V1, that thing. Okay, just in overhead insulators, V2 equal to V1 into 1 plus K, V3 equal to V1 into 1 plus K into 1 plus 3K, that thing. I am not going into that detail. You have studied them in overhead line insulator. Okay. So let us apply that here also, that concept. So from this relation, it is evident we can write V2 minus V1 divided by R1 equal to V1 by R2. Second terms and third terms we are taking. So just separate V2. We want V2 in terms of V1. So V2 by R1 equal to V1. Take a common 1 by R2 plus 1 by R1 equal to V1 into R1 plus R2 divided by R1 R2. So V2 itself is R1 gets cancelled out, V1 into R1 plus R2 divided by R2. Okay, equal to V1 into 1 plus 1 by alpha, because we know that what is alpha. Alpha is the ratio between two radius. Okay, already we have discussed that. So if we want to express V2 in terms of V1, that will be V1 equal to V2 into alpha by 1 plus alpha. Okay, remember this as a equation. Let it name expression A. Again, from this relation, if we take the first and second terms, then we can easily have V minus V2 divided by R equal to V2 minus V1 divided by R1. Now what do we want? We want excuse me, we want the relation between V and V2. Already we have known that V1 in terms of V2. So you apply this equation over here. I am not doing that. I am not going to do that. You will practice it by yourself in home after watching this video. Give a pause to this video, try to derive it out. I will be writing the final result. Okay, because this is a simple mathematical expression analysis, so I hope that can be skipped at your level at least. So just putting the value of V1 from this expression A, and separating the terms V and V2, we can write that V equal to V2 into 1 plus alpha square divided by alpha into 1 plus alpha. Okay, or in other words, V2 equal to v into, take alpha common, 1 plus alpha divided by 1 plus alpha square. Okay, so let's name it as equation number B. Excuse me. Now we have obtained v1 and v2. We have obtained v1 in terms of, in expression A, and in expression B we got two substitutions. Now from A and B, that means substituting v2 from relation Gmax equal to v minus v2 by r ln alpha. Then what we can write? We can write that Gmax is equal to v minus v into alpha plus alpha square divided by 1 plus alpha square whole divided by r ln alpha. That means v by r ln alpha, and okay, no further simplification is required. This is your relation. If you simplify this, you obtain something. I'm not going to do that again, it will take huge time. Okay, so gradient at conductor surface without intershade, that is what G equal to V by R ln R by R equal to V by 3R ln alpha. Why am I writing that? Capital R by small r equal to capital R by R2 into R2 by R1 into R1 by R. So it is a alpha cube. If you take a logarithm of that, it becomes R ln alpha cube. So it becomes 3R ln alpha. Okay, that's the thing. And here if you simplify, I forget to write that. Excuse me. If you simplify that, it becomes V by R ln alpha and there will be one term into 1 by 1 plus alpha square. Okay, so that is the scenario. And from cable geometry, alpha is always greater than 1, that is evident. So the gradient with intershade is lower than without intershade. Okay, why? G max by G, that becomes what? 3 by 1 plus alpha square. Okay, so this relation you should remember. G max by G equal to 3 by 1 plus alpha square. Okay, so gradient with intershade is lower than without intershade for the same overall size and operating voltage of the cable. Okay, so this is what we were trying to prove. So this means that a cable of particular size can be operated for higher voltages, or for a particular voltage the size of the cable can be reduced. The voltage of the cable with this interseed arrangement can be obtained easily. Okay, let me write that now. Voltage of cable with intersheet, SHEATH, with intersheet equal to V, that is equal to G max into R ln R1 by R plus R1 ln R2 by R1 plus R2 ln capital R by small r2, or in other words V equal to G max ln alpha, take it common, R plus R1 plus R2. This is ln alpha, this is ln alpha, this is ln alpha. So ln alpha will be common, that will be R plus Rn, R plus R1 plus R2. So that is the expression right now. Okay. Now there can be other arrangement of intersheets as well as insulating material thickness between successive intersheets. Okay, the grading theory is more. Now listen to the conclusion what we have done so far carefully. The grading theory is mainly theoretical interest. The grading theory is mainly a point of interest from theoretical point of view only, than practical. Why? Because capacitance grading is difficult. Why? Because non-availability of materials with widely varying permittivities, like epsilon 1 is much greater than epsilon 2, that is hardly possible to find. The second reason, that with time the permittivities of the materials may change, as a result which may completely change the potential gradient distribution and may even lead to complete rupture of the cable dielectric material, okay, at even normal voltages, due to aging mainly. You know that due to aging properties degrades, so permittivity also degrades, and Today you are using one cable at say some certain amount of voltage, say 132 kV. After 10 years, that 132 kV may cause damage to your cable. Okay. Now, in case of intersheath, there is a possibility of damage of intersheath during laying operation. That means when cables are buried underground, when cables are laid. And besides, the charging current flows through the intersheath also, which in case of a very long cable may result in overheating. So for these reasons, modern practice is to avoid grading in favor of oil and gas filled cables. Okay. So for gas and oil filled cables, grading is generally trying to be avoided. Okay. So that's well for the class for this session. Next we will be coming with the new topic, and I will be attaching some numericals as an assignment. Only 2 or 3 problems will be there, so don't worry for that. Thank you.